Hey guys, Mr. LaSure here. I'm going to work out a Newton's second law problem which involves kinematics as well. This is from the forces unit on positive physics. It's a challenge problem set. 70-kilogram bicyclist initially at rest pedals to the right, generating 250 newtons of force for 4.9 seconds. During this time, she experiences 50 newton of drags. Neglect any friction impeding her motion. So first we need to figure out what the magnitude of the net force is, and then the magnitude of her acceleration. We're always going to begin these problems by drawing free body diagrams of the system. So here I'm representing the bicyclist as a dot. We know that the bicyclist has a normal force up. We know that she's got gravity down. Here she's generating a force applied to cause her to move, and then there's going to be a little component of kinetic friction acting against her. Right. After you have a free body diagram drawn for the system, the second step is always to use Newton's second law and analyze the forces. So we'll do the sum of the forces along the x direction first, the horizontal. That's equal to the force applied minus the force of kinetic friction, and that's all equal to mass times acceleration in the x direction. We can then plug in some numbers. We're told that the force applied is 250 newtons minus the 50 newtons of drag equals the mass of the system, and her mass is 70 kilograms, times the acceleration in the x direction. We'll then go and solve. 250 minus 50 is 200 newtons equals 70 kg times AX. So the sum of the forces, what's the magnitude of the net force? Now the magnitude of the net force, as you can see, is 200 newtons. What is the magnitude of her acceleration? We're just going to solve for A here. I'll divide by 70. Divide this by 70. We get 200 divided by 70 equals 2.86. So 2.86 meters per second squared is equal to the acceleration in the x direction. We're going to put that up here, 2.86 meters per second squared. Now that we know how fast she's changing her velocity in the x direction, we can come over to this part here. We're told that we need to figure out her final speed and then how far does she travel during this time. So we know here v naught is equal to 0, and then she's got some final speed here equal to question mark. We know this all happens over a time interval delta t equal to 4.9 seconds. So I'm going to go and use a kinematic equation. We know that Vf is equal to V naught plus A times T. Vf is what we're solving for, equals V naught was 0, plus our acceleration in the x direction from part 1 is 2.86 times the time interval, which is 4.9 seconds. Take 2.86 times 4.9. We get 14.01. So her final velocity, therefore, is equal to 14.01 meters per second. 14.01 meters per second. And now we're asked, how far does she travel? Well, we have a relationship that says delta x equals v naught x times t plus 1/2 at squared. Because v naught x is 0 times t plus 1/2 at squared, this simplifies out to delta x equals equals 1/2 times at squared. Plug in our variables. Delta x is therefore equal to 1/2 times our acceleration, which is 2.86, times our 4.9 squared. Come and plug it in. 2.86, clear that. 2.86 times 0.5 times 4.9 times 4.9 equals 34.3. So delta x equals 34.3 meters. 34.3. So just to recap, step 1, free body diagram. Step 2, Newton's second law. Sum of the forces in the x, sum of the forces in the y equals mass times acceleration equals mass times acceleration. Step 3, typically solve for a. And 4, use the kinematic equations to solve for unknowns. I hope you found this helpful. If you have any questions, please email me.